Then for autocorrelation, for this autocorrelation at zero shift, you just need to calculate second moment. And because we assume that two adjacent symbols or any symbols independent, when you calculate the autocorrelation, any delays between sequences, calculate squared value of first moment. This is fundamental for sequences where we're talking about dependent symbols. And also we say that they stationary. And we consider that we find this discrete autocorrelation function. Then we find via discrete time Fourier transform power spectral density to be just constant. And then you can calculate, that's all, yeah. And then we just compare it how it works for unipolar sequence when you have all amplitudes positive. And then you see that actually in our power spectral density, we get additional DC component. We didn't have it before, and now we have DC component. So we have to spend power transmitting DC part. Then we considered the case where we perform filtering on our sequence, and we check what happened in this case, how filtering influences our transmission. We assume that we have transmission of only two symbols, 1 and -1. After filtering, we see that we have, this is our alphabet after filtering. We have three possible cases. We have -2, 0, and different probabilities. Calculate how autocorrelation function will look like. Original function is just delta pulse. And then in order to find it, we go to frequency domain. We calculate power spectral density as the output by just using property that we need to calculate product between input power spectral density and squared value of transfer function. And in the end, we see that plotted, but the resulting function like this. Fs over 2 should be like this. And you see that actually at the 0, we don't have DC, and then we have just distributed for except DC part. What happens if you plot this graph? And then we found autocorrelation function calculating transform, and this is how autocorrelation function looks like. Was what we did last time. Any questions? Not? Okay, we're going to continue, and we start with task number 4.4. If we have time, we come to task 4.3, but we start with 4.4. And if you have any questions, you are welcome to ask the chat. You can also try to open your microphone, but our experience is not very good. Yeah. So, and for this task, for task number 4.4, we consider a pulse position coding, and we use it to ensure DC balance. And we use the following lookup table for coding process. Use for every 2 bits, or every 2 bits in our sequence, we replace by 4 output. Samples or snapshot. So we have, let's say, bits. Just repeat for our table. We have bits, bit 1, bit 0, bit 1. We have the following lookup table. We have 1, 1, 1. So we have 4 different options for 2 possible bits. And for each pair, we start with 0. X0, X1, X2, x3. So if we transmit two symbols 0, 0, then we, at the output, we have the following sequence. 1, 0. If we have sequence 1, 0, after this form, we transmit sequence 0, 1, 0, 0, and so on and so forth. For 2 bits 0, 1, we have sequence 0, 1. And for sequence when we have two ones, we transmit 0, 1. This is what we transmit for different situations. This we call as coded symbols. Coded symbols. So now we need to determine autocorrelation function. And I have to say that this is not stationary process. This is it's not the stationary process because, of course, we look to symbols, samples within one coded symbol. Then, of course, you have strong dependency on what you transmit, what is the value you have between samples. And for this reason, this such kind of process called as not as, but as cyclostation, because you have some cyclic structure. And now we try to reveal structure or what happened. So in order to do this, let me do the following operation. Yeah. First of all, we say that we need to find autocorrelation function. But for this case, I mean, I ask you, in general, when we talk about stationary process, how many arguments you have for autocorrelation function in order to determine it? Or in general, previously, how many arguments did you use to describe autocorrelation function? One of these options. Well, I mean, it was recently. Like, for example, this one. How many arguments you have to describe this function? Where you have second? Check. Chat. The question for 1, 0 bits combination coded symbols are 1. Okay, yeah. But it's not a conceptual problem. And we have only one argument. Just define L. Is it 0, 1, or 2, or any integer number? Then you get value for autocorrelation. Happens for stationary process because for autocorrelation depends only on shift, but not on absolute, not in index where you measure this autocorrelation. What's important is what's the offset between two sequences that you evaluate. But here we have different situation. Here, our autocorrelation also depends on index where we measure our autocorrelation. And also it depends on the shift. So we have two arguments. We have M and L. And we try to, M is how we can call it? M we can call as absolute index coordinate, and L is shift in sequences that we have. That you shift it by 0 samples, by 1 sample, 2, 10, and so on. So we have two parameters. Now let's try to answer the first question. For the first question, we need to determine the autocorrelation function of two arguments. But okay, in the task it's written N and M, but it's not a conceptual. Consider the autocorrelation function for M equals to 1, 2. Depends on the actual time index N in the coded words all realizations, I assume it to be synchronized. Okay, maybe in order to avoid confusion, I have to use the same indices as in the task. Let me change. Let's call the absolute index will be as n, then shift we call as m. Then but it's not a conceptual problem. Okay, and now we say that idea that you need to consider synchronized sequence of blocks. Of blocks. And what it means, remember that when you calculate statistical parameters, you perform averaging over realizations. So what it means, that let's say you have a device that produces you coded symbols. Then you come today to the office, your office, and then you switch on this device. And you measure from the very beginning after you switch it on, what will be the output sequence. And let's say you have a sequence, just arbitrary sequence. And first you have block B1. This upper script, superscript means that it's first realization. Then you have block B2. Then you have block B3. And infinitely many blocks. Then you come tomorrow to your office. You take the same device, you switch it on, and you measure next sequence that it will produce. But we say that we have synchronized sequence of blocks. It means that yesterday you started measuring at the beginning of your blocks, and then today you also start this beginning of your blocks. But of course, sequence itself can be different. You don't know what will be the sequence. So let's say it will be B1, B2, B3, like also. I mean, it just denotes sequence, but values may be different. Superscript 2 means that it's like today or yesterday or tomorrow. It's the time instance. And then we perform this procedure multiple days. Always start recording our blocks when symbol itself starts. And symbol starts. 1 n, 2 superscript n, p3 superscript n. So, and then when we ask you to evaluate statistics, ask you to evaluate, you perform averaging or you perform evaluation over realizations. And what it means, that you just take first position, first sample for all sequences, and then you calculate whatever statistics values, and you average all realizations, variance, then you calculate square average. Else you go for all realizations for first sample for all sequences. This is how you perform averaging. This is what we consider now, and this is called synchronized sequence of blocks. So you see that all blocks start at the same moment. Of course, block itself may contain different coded sequence, but always start recording at the beginning of this sequence. And this is what we call synchronized. And now let's try, I give you just the arbitrary sequence of and we try to understand what will be the autocorrelation for this synchronized case. Just show that we have symbol, sequence of symbols, and sequence of symbols, and then let's say third one. So, and I just give you random realizations randomly, without any. It's not given in the task. It's just I just by myself. So, and we have block number 1, 2, block number, and this is sequence x of m, x of m. Because defining index m, you get what's the value of this. And now we need to evaluate. Now we need to evaluate correlation. And what usually you do for when you calculate autocorrelation, take your sequence, you make copy of your sequence. And then what you start doing, you start shift one copy relatively to another one. And then what you do, every time you calculate element-wise product and calculate what's the overlapping area between these two sequences. And here we do the same, but surprisingly, our autocorrelation depends not only on the value of shift between sequences, but it also depends on the place where you start measuring this autocorrelation. For which point you calculate autocorrelation. And let's try to check how it works, actually. You consider first autocorrelation for, it's not, sorry. Sorry for the confusion, because I have to change parameters. We use n, and our shift will be m. Sorry, absolute index m. Shift will be m. So let's consider when we have shift equals to 1, and what happens. So what will be? We consider synchronized case, and you consider first symbol. Let's just limit ourselves by first symbol. And then for first symbol, no, because it's artificially constructed by ourselves, that if you have a position, if you have one at specific position, what will be for all? Let's say if you have one at position number 2, and you have anything different from 0 for position 1 or position 2. Yeah, because I mean it's determined by our design, that we say that these 4 samples, they define our symbol. And if we have one at position number 2, for all remaining 3 positions, it will be always 0. And then what it gives us? It gives us that if you have, it just says that actually, if you have one at position at one place, at any other position that far apart, like that, by one sample apart, you always have correlation equals to 0. Why? Because always you have, nearby you will have value 0. Cannot have anything else. But only for this specific case, when n, let's say, when we only consider these samples within one symbol. So if you analyze what the correlation between first sample and second sample, always will be 0, because if first sample equals to 1, second sample always equals to 0, and vice versa. If second sample equals to 1, if second sample equals to 1, first sample always will be equal to 0, because it's defined by our design. And there is nothing to discuss. We say that this first case corresponds to n equals to 0. n equals to 0. Then if I consider next next pair between second sample and the third sample, front. Because the same, I mean, still within the same symbol, and I mean, also it will be 0, but we just say that this case for n equals to 1, n equals to 0. Then let's consider next, actually I should save space, 1. Then for n equals to 2, and also for n equals to 2 and m equals to 1, the same story. Autocorrelation equals to 0. And then we come to the interesting case. We have the last sample from first symbol and first sample from second symbol. Situation different. Why? Maybe you can use microphone so that everyone, but please unmute it first.
Because if the last code is of the block 1 is 1, we can get the block 2 first code also 1.
Yeah.
That is not 0.
Yeah, I mean, because two symbols independent, coded blocks independent, and as a result, we can encounter situations. Last sample at first symbol will be 1, and first sample at second block will be also 1, because they're independent, and sometimes it happens. But okay, but what's the probability? Okay, first question, what's the probability that first block will contain last sample equals to 1? 1 by 4. And then it's very easy to answer what's the probability that first block will contain 1 at the last sample, and second block will contain 1 at first sample. You already have half of the answer. 1 by 16, because they're independent. And I mean, for first block, probability will be 1 by 4. Second block, it will be 1 by 4. And then you multiply. They're independent. And probability that these two symbols will contain 1 over 16. So, and this happens for m equals to 0, 1, 2, equals to 3. Okay, and yeah, it's not so interesting, but let's continue. What happens if we have n equals to 4? And you see that actually story repeats, that we have the same, because we're working within one symbol and nothing changes. So for n equals to 4, we just have a repetition of the same story that we had before. And let me write on the right side result that we actually get. So what we should write? We should write the following, that for m equals to 1, autocorrelation that we find as x of n conjugate times x of n. In general, we put conjugate, but of course it also applied for real valued signals. And here we write our autocorrelation as combination of different cases. So we have first option, that autocorrelation equals to 0 for fifths, no, not n, for n equals to 1, 2, 0, 1, 2, and then 4, 5, and so on. So you see that we have this they repeat specific period. So, and you can even write it as 0, 1, 2, and then we can write plus we just introduce just can put any index and you understand what will be for which absolute indices you will get this autocorrelation. And it equals, this autocorrelation equals 1/16 for n equals to plus 4k. So if you substitute k 3, then it will be 7, 11, and so on and so forth. This is what this is autocorrelation for m equals to 1 and different values of n. Not, it's for different values of n, and shift between sequences equals to 1. Okay, now let's go further, and let's analyze what happens if m equals to 2. M equals to 2. So what we do? If we take n equals to 0, we analyze first sample and sample number 2. Sorry, 3. First sample and sample number 3. And again, what will be the autocorrelation? 0. Okay, then we make shift. We start with n equals to 1. Then we take another sample that 2 samples apart. And again, what's the answer? Because we're still within one coded symbol. Out of 4. And it will be repeating this period 4. Because if have situation that wherever you take symbols at edges, like for sure it will give you, like always it will be equals to 1, then instead of 1/16, put 1. And because actually out of 4 cases for both take only one case, 1/4. As a result, in many other cases, in 50/16, because they just different, only in 1/16, it will be the same, and it gives. But I mean, you can say that 15/16 will be equals to 0. Because I mean, if always it would as 1, then we would write 1. Because we're working with alphabet 1 and 0. You can write like what will be the how to find this 1/16. It will be 1 times 1/4 plus 0 times 3/4. How about it will be 0 times 3/4? 1/4 times 1 plus 4 times 0. Maybe it helps you if you have different alphabet, like 1 minus 1. But for us, you can just ignore it. Then it equals to 1/4. And then the same will be for adjacent. We'll have 1/16. But it's a good question because you keep in mind that if you have different alphabet, result will be different. Okay, so we see that for first 2 cases, for n equals to 0, n equals to 1, we have get the same result that autocorrelation equals to 0. Then something happened, something interesting happens. I take third sample from first block and first sample from second block, n equals to 2. What happens? Because not 0, because we have two independent blocks. Blocks independent, and the result of autocorrelation will be the same as for 1/16. Because again, because this sample is absolutely independent. And what's the probability that you have something non-zero for third sample? 1/4. 1/4. What's the probability that you have something non-zero first sample of second block? Also 1/4. Then you multiply this. I should start answer for m equals 2. And then we have 1/16. Now we have case n equals to 2. Let's check if we have more options. And then we are going to consider next case. So we start with last sample from first block and the second sample from second block is n equals to 3. Get exactly the same result, that you have two independent samples. And probability will be again 1/16. Say that 1/16 autocorrelation not only for n equals to 2, but also for n equals. And yeah, I mean, and if we continue, if we take n equals to 4, then we come to the same result as we had for n equals to 0, because we have two samples from the same block, and they independent, autocorrelation will be equal to 0. We can write that we have 0 for indices 1. We can just repeat period 4 for. And you see why it's called cyclostationary, because parameters specific period, or they cyclic. Let's continue. Then we go to n equals to, let's say. So again, we start with our first sample. I take third sample. I still within one block. No, it was 1, 2. No, it's fine. Yeah, it's fine. It's 3. And we have n equals to 0. Yeah. And we still within one coded block. As a result, we can also start writing answer for autocorrelation. M equals to value of. Actually, I should write it as xn plus m. It will be forward. Otherwise, it's just second moment. So we have 0 for n equals to 0. Okay, let's see what happens. Then I start with second sample, and when I take 3 samples apart, come to second symbol. And I mean, discuss that 2 samples independent. As a result, there is samples also. And we have autocorrelation will be 1/16 for n equals 1. Then this is. Then if we make by one more sample, n equals to 2, again, we actually see that we have two independent blocks. And again, cross correlation will be equal to 1 over 16 samples because they're independent. And then we can just make one more, n equals the same story. And for n equals to 4, this is only one case. And we staying within one ordered block. You can say that, oh, this 4k. Last case that we have to consider is case for m equals to 4. Okay, let's try to check what happens. We start this sample. And happens m equals to. Yeah, I mean, immediately you see that actually for m equals to 4, actually I can write for m larger or equal than 4, always will be analyzing independent samples. And regardless on shift n, we always have the same autocorrelation. M equals to 1 over 6. Have any n questions in the chat? Okay, why we have 1 over 16? As we discussed, it was previously that 1 over 16 is nothing else as second moment. Oh no, it's not second moment. It's have this. What's the probability for one position? For one position, have one non-zero element. Probability will be given by this expression on the right. Probability that we have non-zero component. It will be 1 over 4 times 1 plus 3 over 4 times 0. And equals to 1 over 4. But then what's the probability that two independent symbols equal to both of them will be non-zero, both of them. And the probability, just take probability for first symbol that is not equal to 0, and probability that for second symbol it's also not equal to 0. As a result, probability that both of them, the xn equals to 1 and m 1 over 4 times 1 over 4, 1 over 60. But only if m large enough so that you have observing independent samples. Because if they one symbol coded block, of course the result will be equal to 0. Okay, this is the idea. Or determine autocorrelation function. And this is actually the answer. You see that the autocorrelation function is given by this write it for this combination of these expressions where for different have different options depending on your absolute index and shift you get nulls. Okay, but now we come to second option. Now we try to get or we need to simplify this expression, and for this we consider its part B determines the time averaged autocorrelation function, which is identical to the autocorrelation function of the stationary process or unsynchronized stationary process with the random variable theta that defines phase of our block code. And actually what it means that we have unsynchronized or non-synchronized. Let me another picture. Part B. Now we consider non-synchronized here. Synchronized sequence of blocks. And it will help us to simplify expression. Again, I show arbitrary sequence of blocks. Let's say first sequence will be catch it at beginning. Upper index is index for realization. B1, B2, B3. Then for second part, we started somewhere in the middle. Okay, I use slightly scaling, but we have 4 samples for each symbol, and we have 4 different options phase. But let's say we missed first 2 samples and we started in the middle. This is how we start capturing our part of sequence B1, 2, this B2, and B3, and then we have B4, and so on. First case, and for another case, let's say we start capturing right after first sample. B1. B2. Then B. And now you see that when we calculate statistics over realizations, we don't know what's the value of M absorbing. Don't know. We can control over only. We have control over only shift between sequences, between sequences. But we don't know what's the value of M we have. N absolute. We don't know what's the absolute index N, but we know shift M. Sorry for this confusion. Sequence X of N. As a result, now when we calculate this averaged autocorrelation function, we have to average over what happens, average over different absolute indices N. Then we provide this time averaged autocorrelation. So this is what. But is it clear about this idea that previously sequence was synchronized? You always knew that if you have capture your signal, you always start it. But now you don't know where is the beginning of your sequence. You can start somewhere in the middle, and after first sample, And you have 4 options where you start capturing your signal. You can start after first sample, or second, third, or last one. And now we need to calculate this average it. And then we get our relation as function of only index of shift between sequences, only as function of m. Now let's try to analyze. First, I need to find my mouse. Okay. So, what happens when m equals to 0? M equals to 0. Then again, you just do simple math. Have this expression? No. No. Yeah, we forget to discuss. To discuss what happens when m equals to 0. What happens when we don't have any shifts? When we just analyze our sequence and calculate squared value of the sequence. And what will be the second moment? I mean, just imagine you have this sequence, 1 by 4. Because I mean, you have this sequence, and you know that each block independent. And then when you calculate, you need to calculate square value of this sequence. But for this specific case, you have just 0 and 1. So if you calculate square, it will be against 0 and 1. And then there's the question, what's the probability that you have non-zero result? It will be 1 by 4 because each block independent, and within each block you have only one non-zero element out of 4. So we should put somewhere that for m equals to 0, we have 1 by 4. Have 4. Close to 1 by, and you see that it doesn't depend on, because it's just sequence. Why the last element of the third block is equal? Why the last third block? No, it's not 2, it's my 1. Sorry for this. Now we can continue our investigations and try to understand what happens for non-synchronized case. And same idea, that what happens, now you analyze, just take this cut of different realization, and you have the same question. You calculate squares of all these sequences. Then you calculate how often you will counter non-zero element. Answer. But I mean, remember that for this specific case value, doesn't change. And the question, okay, now you are not synchronized. You have different random shift. How often you will encounter one? Just take this cut and just one by four. Exactly, it's 1 by 4. Why? Because we say that all these shifts have the same probability. As a result, when you shift, I mean, you doesn't change, I would say, you don't change any properties. In general, you have just the same probability that you encounter one, because it will be just the probability that, for this case, you can do the same as if you would just take analyze sequence. But for m equals to 0, probability doesn't change. Equal to 1 by 4, counter 1. Well, idea was the following, that if you just take first symbol, have, let's say, 0, 1, then you say, like, have 1, it was fast. One. And you continue writing these random sequences. 2, 1, 0. Just take all these samples. Because all these possible shifts, they equally probable. They don't change probability or they don't change frequency. How often you see one first position? Just what happens that already have specific probability. What probability that one occurs at one position, and then sorry. No. We say that it was the end of first, yeah, and then beginning of next one. Because now we say that it's not synchronized. Sometimes you can have, don't know where's the start, where's the end. Yeah, this is what happens. That because shift is equally probable, I would think that we can even write it in a formal way, something like probability of shift times value of value, and then you can justify it. But we don't go there. You just check it at home, or believe me, because it's better if you check it at home and think about it. That, yeah, maybe it's good if you think about it at home, and then we can come back to this discussion. But have random shift, but we're talking only about first moment. Talking about case when shift equals to 0, only about m equals to 0, but not for all other. For the rest, have different results. M equals to 0, we say that this averaged autocorrelation equals to 1 over 4. Okay, then m equals to 1. Or I think, okay, after we consider case 1, maybe we can actually go back and I try to just, okay, now we analyze, oh, yes, m equals to 1. We analyze what happens for when we have shift between delay, between sequences equals to 1. And we don't know where we have start of our symbol, of our block. And this is what we have to consider our for m equals to 1. And you have to average, calculate average. In average, what will be the autocorrelation function? Because in general, how you have 4 cases that you can see. You have 4 different cases. You have n equals to 0, n equals to 1, n equals to 2, n equals to 3. And n equals to 4 is the same as n equals to 0. Then what in average will be the probability that you, because in cases out of 4, observe, and in one case out of 4, 1 over, what will be the average? I mean, if you, because you don't know what's the value of n, have random starting point where we measure average 1 by 64, because only in one case out of 4 have something non-zero, and for all other 3 cases have 0. Then what you need to, actually it's what happens for m equals to 0, because for m equals to 0 we say that for n equals to 1, 2 plus 4k, regardless on absolute x, always have the same autocorrelation. Then my question, what will be the average? That you don't know what's the, where is the beginning block, and you calculate in average what will be the autocorrelation. All for 4 cases you have the same value. As a result, in average you have this value. For second, for m equals to 1, you see that we have non-zero component only in 1 out of 4 cases. This is, by for first case it was 1 over 4. For second case, we calculate it as 1 over 4 times 1 over 16 plus over 4 times 0. And it gives us 1 over 64. We can also rewrite first value as 16 over 64. And we continue, and we write for m equals to 2, average it autocorrelation function. And what will be the result? In 2 cases, have that autocorrelation equals to 0. And for other 2 cases out of 4, autocorrelation equals to 1 over 60. And we calculate, I mean, in average, if you don't know, because non-synchronized case means that you don't know is it end of your symbol, you don't know if you're analyzing random blocks or you are same samples within one block, and we have to say in average out of this autocorrelation. Of course, you just take 2 times 1 over 4. No. You have 2 over 4 cases for 0 and 2 over 4 cases for 1 over 16. You have 2 over 4 times 1 over 16 plus over 4 times 0. And it gives us 2 over 64. This is our average autocorrelation. 2 cases out of 6 have something non-zero when m equals to difference between sequences equals to 2 samples. Then for m equals to 3 to be over 4 1 over 6 plus 1 over 4 times plus 3 over 6. Last, for m larger or equal to 4, average output will be that always we analyze different samples, and for all of them we have 4 plus 4 times 0. Then it gives us 4 over 60, or 1 over 60. For m equals to 0, let's say we have sequence 1, 0. First block, second block, 1, 0. This is x of n. Then what will be the sequence x of n squared? X of n squared for this specific case will be exactly the same sequence because you have only ones. This is your squared sequence. Then my question, what will be the autocorrelation function at 0 for such sequence? And in order to answer this question, calculate probability that have value sequence. And probability for this autocorrelation for 0 will be probability that you have 1 times value plus probability that you have 0 times value equals to 1 over 4 times 1 plus over 4 times 0. 1 over 4. Why we get 1 over 4. But you should be careful if you have slightly different sequence, of course the result will be different. Very simple outcome we have only for this value 0. Okay, so and now I think now we need to plot it because now we have everything what we need. We know how autocorrelation function behaves for 1, 2, 3, m larger than 4 or equal to 4. Link. They will cover over 64. Then here we have autocorrelate. One. What's the value for 1? 1 over 64. Let's say it should be somewhere 4. For 2, it will be over 64. For 3, over 64. And for 4, it will be 4 over 64. For 5, 6, 7, it will be the same. The same for negative range. 1, -2. One, 64, or 64. Constant. This is how it looks like. Have this autocorrelation function of shift. So and you have homework. You have homework. You need to try to simulate this autocorrelation function. Try to obtain what by a numerical simulation. Because I think it should be available on Moodle both for Yodogram, but it's for and then you need to replace this symbol by this block. Try to analyze what happens. Okay, any questions for this task? To have some time to ask next question. Let's go to question 0.5, I think is okay. 5 and then 4.6 have time. Consider, for 4.5, we consider an ideal time low pass filter with transfer function, and then we can triangle. So assume that white noise, the power spectrum density, as a constant power spectrum density, and not by 2. And we have such unlimited frequency range from minus infinity, and power spectrum density is constant. By the way, what's the of such a noise? What's the energy? For some reason, ask you calculate energy. Sorry? It's infinite because you remember that you calculate energy as integral from minus infinity to infinity of power spectrum density. Here we have constant power spectrum density for all frequencies from minus infinity to infinity. As a result, if you try to if you disturb the turn, because infinite energy. Of course, in reality, it doesn't happen because whatever you place, you will have limited bandwidth. As a result, after you apply it, filter or whatever, this white noise becomes band limited noise. Have finite energy, because finite bandwidth. But for this abstraction, you have infinite energy. And we need to determine autocorrelation function and power spectrum density of the output signal. And then we need to determine RMS value of the output signal. Root mean square value. So, and try to work. So we have rectangular window, f divided by 2, our transfer function. Fg equals 5 megahertz. So, and we assume that power spectrum density by 2. And our filter or our block may be characterized by 2 parameters, either transfer function or impulse response. We have transfer function, but then we can calculate response. Transfer of t. But then we have to calculate convolution. X of f, or we can also characterize it in time domain. X output, I of f. Remember that if we want to find autocorrelation function or power spectral density, autocorrelation function of output signal can find as convolution between autocorrelation function of convolution with autocorrelation function of filter. Or we can find, by the way, we also impulse response, it will be energy autocorrelation. Or we can actually find, instead of autocorrelation, we can power spectral density of output signal as product take f model square times f of x, fxx of f, phi of fxx. And we can just take a look and see that actually we already have transfer function and we know what's the power spectral density. Just use second option, calculate output power spectral density. Output power. And if we calculate inverse Fourier transform, then we get autocorrelation function. Right, that output power spectral density. We can write, then we calculate square value of rectangular window, act f of model squared times and naught by 2. Thus, you see that we just have a naught by 2 times rectangular divided by 2f tau square, because rectangular function has value 0 or 1. Now we need to calculate inverse Fourier transform in order to determine autocorrelation function. Go from frequency domain to delay domain. And here we have function from the of our basic transforms. Have one domain, we have pillar shape function dimension. In opposite domain, it will be. And we say that we get function fg times n by 2 and times c function. Function of pi tau and random. Get n0 times fg times psi function times fg. How our autocorrelation function, like our power spectral density. Very simple. The next question will be, you need to find so-called RMS value, root mean square value, because also we have RMSE, root mean square error. Simply calculate what's the meaning of RMS? Have any physical notion for this? How we calculate it? But what's the, let's say, observe signal and then someone tells like, oh, calculate RMS. Get some like something, you get like value 5. What it tells you. Well, sorry? I would say definitely can get RMS without DC. Don't have any DC component, you can calculate non-zero RMS is the root from variance. This is standard deviation. Directly relation to standard deviation. It tells you in average what's the fluctuation of your signal. And yes, it's also, we can say that it's related to this. Because, okay, yeah, because also very often what you do, you subtract mean value. You subtract mean value, but here we don't do it. And then probably you're right. Let me just probably characterize. Case if you have DC components, then you characterize DC component. But if you don't have DC components, then you characterize what's the variance of yours. Can say like this, because in the end we see that actually this RMS will be proportional to autocorrelation function at zero. If you don't have zero, or if you don't have DC component, it's not necessary that autocorrelation else as variance. So now we can say that our RMS find integral. We have two options. We can calculate either integral in time domain, or we can calculate integral in frequency domain. And if we calculate, so what we have to do, we have to take our signal, calculate square value, and then integrate over all range of our signal. Minus finish to, and what we get, we get nothing else as energy of our signal. But then we have to calculate square root from this signal result, get amplitude. If you remember that this has definition of autocorrelation at zero. Because you can assume it as integral for autocorrelation for shift that equals to zero. On the other side, you can calculate the same RMS value, as I said, by frequency power spectrum density, x of f value squared. Then you integrate it over all range of frequencies, calculate square root. And this value of x of f without integral, our power spectrum density, Ixx. So, and we can simply use first, because it's autocorrelation at 0 point, and we already know what's the autocorrelation. And even if you would use power spectrum density, also can easily calculate this integral because you have a rectangular window. You can write that our RMS equals to phi at 0 under square root. What will be the result? We just take out the correlation function and naught times fg times phi function 2i times phi function equals to 1 at 0, come to the answer times fg. And you see here that we don't have DC component. Do we have DC component for this example? We have noise. Noise, I mean no DC component. Because mean value for noise But here you see that even if I don't have DC component, variation, you have this, you have non-zero variation. And this variation proportional to bandwidth that you have. Because larger bandwidth, this parameter, FG, larger bandwidth, larger RMS value you have at the output. But of course, if you have DC, you have additional part for DC. Then actually you will have mixture DC plus. But usually we try normalize and subtract DC. For us, it's often it's important to know what's the variation of self. Okay, yeah. Any questions? Oh, then actually we still have time to go for task number 4.6. So for 4.6, we consider first order low pass filter, and we have filter impulse response. And we say that at the input of this filter, we have again noise, and we need to determine power spectral density at the output. We need to determine RMS value as function of 3 dB cutoff frequency. And then we need to, and then we have like tricky question, what happens, change structure of our. RMS is root means square value or squared value. Calculate square value, then you calculate mean, then you calculate square root of the result. Actually, it's standard deviation. Go for 4.6. Have other questions. So we have following impulse response equals to S of t times 1 over exponential over capital T. If I plot this impulse response goes from 0 to plus infinity. All 0 is value 0 because it's defined by this step function S of positive range exponentially. Our function time and the maximum value 1 over t. Okay. We say that at the input have noise with power spectral density n0 by 2. And we need to determine power spectral density at the output. Now we need to understand how to find power spectral density at the output. And I mean, we can just use the same hint as we did. That output autocorrelation function equals to evolution between response. Autocorrelation of input. Or we can calculate Fourier transform and say that the output power spectral density can find as square value of transfer function, absolute value square of transfer function times power spectral density of phi xx of f. And typically, typically it's easier to do for transfer function, but actually for this case, you can also calculate what the autocorrelation for delay, for noise, the delta pulse. But let me see what we need. But then anyway, we need to determine RMS value. I think it will be easier for us if we, because and also it have to be function of cutoff frequency. Plus, it will be easier if we still keep analyzing in frequency domain. But in order to do this in frequency domain, we need to find transfer function in frequency domain. We need to calculate the inverse Fourier transform of transfer of impulse response. So now we need to still going to the frequency domain way. But for this, we need to find the transfer function. Calculate integral I minus infinity t, and then we multiply by exponential function. Function minus j f t. What happens with integral after I substitute g of? Do we have any changes in the integral? Yeah, we change limits because g of t, our impulse response, exists only in the range from 0 to infinity. So we say now after we substitute, we get integral from 0 to infinity, 1 over t times exponential minus t over capital T times exponential minus j. Now then you need to calculate this integral, but it's very simple. Exponential function, 1 over t, integral from 0 to capital T, and then combine one over t plus pi f. Now what we can do, we can multiply and divide by this also move I mean, there are how to do this. But if we just take brute force way, we can just minus 1 over plus j 2 pi f divided by minus 1 over t plus g f times minus f. So what we are going to do, we're going to move inside differential. Then we can just write that our integral one over, and we can combine e and this denominator. That we have 1 over, no, not t, 1 plus 2 pi f capital T times exponential function minus 1 over t plus j pi have limits past infinity. Okay, when we substitute infinity, have exponential function minus here gives us 0 minus, and then when we substitute instead of t 0, it will be exponential function of 0 plus 1. 1, we have minus in front of the expression. So we come to the function 1 over 1 plus j pi f capital T. And it is function of frequency. Function of frequency with our transfer function. Function looks like. So, but what we need, we find absolute value squared. This is f equals to 1 over 1 plus. You can write that g conjugate f equals 1 over 1 minus. And as a result of f absolute value squared, put to 1 over 1 plus 4, or I can write, yes, I can write 4 pi squared f squared squared. What I can write for our transfer function. How it looks like. For the transfer function, see that it behaves while you increase frequency, transfer function goes to 0 because our g of f value squared. Okay, and now we have everything to find output power spectral density for the for our input signal after the filter. So now we can write that output power spectral density can be written as transfer function more absolute value squared times input power spectral density and not by 2. Input power spectral density. And that's it. This is how our transfer function, how our power spectral density will look like for the output signal. Okay, fine. And now we come to second part for question B, which asks us to determine the RMS value of the output signal as a function of the 3D cutoff frequency of the filter. So, first, what we need to understand, we have two parts. Determine RMS value of output signal as function of 3D cutoff frequency. First, we need to represent this cutoff frequency as a function of parameters. And then we try to represent the RMS value as function of this cutoff frequency. We have two steps. First of all, let's try to analyze cutoff frequency. Just need maybe 5 more minutes. Here we have for f cut, our output power spectral density. And we say that at 0, our power spectral density equals to N0 by 2. And at cutoff frequency, f cut must be 2 times smaller, must be 1 over 2 of value that we have at 0. What we have at 0 is 2 times smaller. So you have to know what is N0 by 2. So what is the value for f power spectral density at 0? And you know what is power spectral density in general? What's the expression for it? And we can write that, we just write power spectral density for cutoff frequency, 1 plus 4 pi f cut square times t square, times N0 by 2 must be equal to 1 over 2 times N0 by 2. Of course, you can cancel 2. And what you get that 1 plus 4 pi f cut square times t square must be equal to 2. And from there, we easily can isolate f cut. Yet, that f cut equals to what? It will be cancel 1. It will be 1 over 4 pi squared under square root. This is how we represent our cutoff frequency. And I think I've made mistake. I forget square value for pi. 4 pi squared. Then we can write it as 1 over 2 pi capital T, our cutoff frequency. Cutoff frequency. And next part we need to write RMS value. Once again, I write that RMS value we can find as integral from minus infinity our signal in. Or we can use frequency domain and integrate particle density u of f and in terms of particle density, just integral particle density and we know our transfer. And here we know, it's not given in the task, but I give you a hint. Because we can calculate integral, such a function that we have above. We can calculate integral, and integral of such a function will be nothing else but arctangent. Let me show you. Calculate RMS value. RMS value. It equals to integral from minus of our transfer function, of our particle density, and not by 2 times 1 over 1 plus 4 pi squared f squared times t squared f square root is our expression. And have the following hint, that if you calculate integral from minus of the following function as 1 over 1 plus x squared x, then the integral will be equal to arctangent of x, or also sometimes it's called tan x. Or more general, it can be divided by a squared plus x squared x from minus infinity. 2 minutes, please. It will be equal to tangent minus 1 of x over a. And equals to arctangent x over a. Okay, unfortunately, we still, let me just finish. 2 more lines. Then we can actually write it as integral from minus infinity and not by 2. We can prepare our expression for simplification. And divide by 2 pi t, 1 over 1 plus pi squared f t, f squared, and times df. And then, actually, we get nothing else as arctangent function. We have a naught by 2, 1 over 2 pi capital T, arctangent pi f capital T. We have to calculate for range from minus infinity. But arctangent, very easy to calculate for plus infinity and minus infinity. For plus infinity, it will be pi over 2, and for minus infinity, it will be minus pi over 2. As a result, integral gives us pi. Then we come to the result that we have a naught by 2 times 1 over 2 pi times pi But you know that this is nothing else. This 1 over 2 pi t is nothing else as f cut. And we come to the result that we have a naught by 2 cut times pi. Final expression for the function of RMS value as function of cutoff frequency. Okay, yeah, unfortunately now we have to our tutorial. Please let me know if you have any questions. You can come after the end. Yes. I would like to wish you a productive rest of the week. Attention. So next week. I tried to upload also previous notes and this next week.